In this video I will show you how to find the domain of a function. Let's observe the function f of x, which is defined as 2x minus 7. By the domain of this function we mean the set of all possible values for variable x that this function f is defined for. In every single case in which you have a linear function like the one we are talking about in this example, the domain is an entire set of real numbers. So the domain is an entire set of real numbers. All the numbers which are in the set of real numbers are finite numbers. So in the interval notation we can write this set R as an interval from negative infinity to positive infinity. Notice here that at the end of this interval we are using parentheses. That means that the dots negative infinity and positive infinity are not included in that set. Only the finite values are included in this set. In every single case in which you have a linear function like the one we are talking about in this example, the domain is an entire set of real numbers. Let's observe the second case, a case a little more complicated than this one, but not for too much. Let's observe the function f, which is defined as x squared plus 3x minus 5. As you can see, in this case, we are dealing with a quadratic function. The domain is again an entire set of real numbers R. If you are dealing with a polynomial function such as f of x defined as 2x cubed minus 5x squared plus 7x minus 3, the domain is again the set of all real numbers, the set R. So if you look at the definition of that specific function that you are dealing with, if there are no fractions, square roots, logarithms, or some trigonometric functions, so if you have a simple polynomial function, the domain is going to be the set of all real numbers. A case a little bit more complicated than the ones we dealt so far is one where the function f of x is defined as 5 over x minus 2. As you can see, in this case we are dealing with a function which is rational. The question remains the same: how to find the domain of this function? In this case we have a fraction, and as you know, division by 0 is not allowed. That means that the denominator of a fraction has to be different from 0. The denominator of this fraction is x minus 2, and that has to be different than 0. This means that x has to be different than 2. As you can see, x can be anything except number 2, as that is going to produce 0 in the denominator, and we are not allowed to divide by 0. If you decide to see how function f is going to behave around number 2, as for 2 it is not defined, so it has no values for this dot, you are going to observe a left and a right limit of function f at dot 2. And you will see that it has a vertical asymptote which has the formula x is equal to 2. The area in which this function f is defined, a domain of a function f, is the set D, which is an entire set of real numbers except this number 2. For all rational functions, you can find their domain by demanding that the denominator of a fraction that you are dealing with must be different from 0. Then you are going to find the values from x that don't belong in the domain. I want to show you how you can write this domain R without the number 2 by using the interval notation. Let's observe the line of all real numbers. On this line x can be anything except the number 2, and let's say that number 2 is here. we are going to denote that x has to be different from the number 2 with this small circle here. And it has to be an empty circle. An empty circle denotes that number 2 is outside of the interval which we need. If you put a full circle, it means that number 2 is inside the interval that you want. So on the far left side of this line, we have negative infinity, and on the far right side of this line, we are going to have positive infinity. X here means that we are reading the values for a variable x from this line. As you can see, on the left side, variable x is inside the interval from negative infinity to 2. Note again here that we are using simple brackets at this position. That notation means that number 2 here on the right side of the interval does not belong in the set of numbers. For the right side of this line, we are going to have union everything from number 2 to positive infinity, as variable x takes all those values. And this is our domain written in an interval notation. Set D, which is a domain of a function f, is the set from negative infinity to number 2, union from number 2 to positive infinity. Let's observe another example. We have a function f of x which is defined as 3x minus 8 over x squared minus 9x plus 20. As you can see, we are again dealing with a rational function. Only this time it's just a little bit more complicated. We are going to do the same thing as in the previous problem. Division by 0 is not allowed, so the denominator of the fraction has to be different from 0. The denominator of this fraction is x squared minus 9x plus 20, and that has to be different from 0. Essentially, we are looking for x values that are going to produce 0 in the denominator. We are going to find those x values by factoring this trinomial, x squared minus 9x plus 20. The leading coefficient here is 1, as you can see, so we can write this trinomial in the form x minus alpha multiplied by x minus beta. These numbers alpha and beta are those values for x that we are looking for. By expanding these brackets, we get this to be equal to x squared minus alpha x minus beta x plus alpha beta, and that is going to give us x squared minus alpha plus beta x plus alpha multiplied by beta. When we compare what we have gotten with the trinomial that we had started from, we can conclude that this negative alpha plus beta corresponds with the number negative 9 from this left side of the equation. And we can see that alpha multiplied by beta, the product, corresponds to number 20. Our job here is just to solve this system of two equations with two unknowns, alpha and beta. So alpha plus beta is going to be equal to 9, and alpha multiplied by beta is 20. This system of equations is easy to solve. We can straight away see that numbers 5 and 4 are the solutions of this system of equations. So let's put that alpha is equal to 5 and beta is equal to 4, and then we get that x squared minus 9x plus 20 can be factored out as x minus 5 multiplied by x minus 4. Of course, there is another method to find these numbers alpha and beta. Let me show that quickly for you. So we are dealing with x squared minus 9x plus 20, and in order to factor out this trinomial, we need to find its roots. The simplest way to find that is by making this to be equal to 0. So let's find the zeros of this trinomial. We are going to do that with the formula for quadratic equation x1 or 2 is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. And when you deal with this, you are again going to get numbers 5 and 4 as the solution. So these two values are our alpha and beta. Remember from the start that our condition was that x squared minus 9x plus 20 has to be different from 0. Therefore, x minus 5 multiplied by x minus 4 has to be different than 0, and that means that x minus 5 has to be different from 0, and x minus 4 has to be different than 0. Therefore, x is not 5 and x has to be different from 4. Let's represent this in interval notation. I like to draw a graph of what I'm doing, and that is going to be especially important in examples that are way more complicated than this one. And those ones we will encounter in the not so distant future. But I digress. So we have a line of all real numbers, and of course we are reading the values of variable x from this line. We have positive infinity at this end, and we have negative infinity at this end of our line. We have two numbers that we are interested in. Those are numbers 4 and 5. Our variable x has to be different from 4 and 5. So I'm going to put an open circle in these positions where numbers 4 and 5 are to denote that. And now let's see what our domain is. For this left section of the line, we have that domain is equal from negative infinity to number 4. For the middle section of the line, we have the interval from number 4 to number 5, and for the far right section of the interval, we have from 5 to positive infinity. Brackets here at 4 and 5 positions are just simple parentheses. That is how we denote that dots 4 and 5 do not belong in our interval. As you can see, variable x can take any number except the numbers 4 and 5. Let's take a look at another example. We have a function f which is defined as a fraction. In the numerator we have 2x minus 3 and our denominator is x squared plus 4. Let's find the domain of this function. We are again using the same procedure. The denominator of a fraction has to be different from 0 as division by 0 is not allowed. The denominator of our fraction is x squared plus 4, and that has to be different from 0. If we take 4 from the left side of the equation and move it to the right side of the equation, remember, if something changes a side of the equation, it changes its sign. So x squared is going to be different from negative 4. 4 was positive on the left side of the equation. It is changing sides, so it has to become negative 4 on the right side of the equation. And here is the catch. X squared is larger than negative 4 for all variable x's which are real numbers. As a matter of fact, for every x which is a real number, x squared is larger or equal to 0. Whenever you square a number, you are going to get a non-negative value. And this is how we get that x squared is always different from negative 4. So this line here, which states that whenever you square a number, you are going to get a non-negative value. Well, this means that whatever value you can choose for x, the denominator will never be 0. Therefore, the domain in this case is an entire set of real numbers. And we can write that in an interval notation from negative infinity to positive infinity and close parenthesis. We have done enough rational functions problems. Let's move now to next chapter. What if you encounter a square root problem? Let's take an example that function f is defined as a square root of x minus 4. How are we going to find the domain of this function? For square roots or any radical where the index number is even, I'm talking about the functions g of x, which can be defined as 2n the square root of x minus 4 when this n is a natural number. You can't have a negative number as an argument of that even root function. For the radicals where index number is odd, like function h of x defined as 2n plus 1, the root of x minus 4, of course this n is a natural number and we can include 0 in that set, argument can be any number. It doesn't make a difference. But for even radicals, that argument has to be larger or equal to 0. As you can see here, we are dealing with the function square root of x minus 4. Our argument for the square root function has to be larger or equal to 0 in order for that square root function to be well defined. This means that x has to be larger or equal to 4. Let's represent this on a line with all real numbers on it. So we have a line which we are reading the values for variable x from. Negative infinity on the far left side and positive infinity on the far right side of this line. Our point of interest is number 4, which is here. X has to be larger or equal to 4. So we have everything that is on the right side of number 4. As you can see, number 4 is included in our interval, and we are going to denote that with a closed circle, the circle which is filled. And we are interested in the numbers equal to 4 or larger than it, which will give us this section here. The domain is then the set V, which is an interval from number 4 to positive infinity. Of course, we are dealing with the finite numbers, so positive infinity is never included in this set. So we are going to denote that with this simple parenthesis. In this case, number 4 does belong in our set, and we are denoting that by using the square brackets on the left side of this interval. Let's now observe a more complicated example now. Function f is defined as a square root of x squared plus 3x minus 28. Again, we need to find the domain of this function. We are dealing with a square root function, so the argument of that function has to be larger or equal to 0. X squared plus 3x minus 28 has to be larger or equal to 0. Let's find the zeros of this quadratic function using the quadratic formula. So x1 or 2 is equal to negative 3 plus or minus the square root of 9 minus 4 multiplied by negative 28 divided by two values of a. So this is equal to negative 3 plus or minus the square root of 9 plus 112 over 2, which is equal to negative 3 plus or minus the square root of 121 over 2, and that is negative 3 plus or minus 11 over 2. So the value for x1 is negative 3 minus 11 over 2, which is negative 14 over 2, and that will give us the value for x1 to be negative 7. x2 is equal to negative 3 plus 11 over 2, and that is equal to 8 over 2, which is going to give us the value for x2 to be equal to 4. On the line of all real numbers, we are reading the values for variable x from it, we are going to place these numbers -7 and 4 which we got. As you can see here on the real line, we have 3 regions. One is left from -7, the second one is between -7 and 4, and the third and the last region is after the number 4. The question is, which one of these 3 regions do we need? We are going to determine that by observing our quadratic non-equality. X squared plus 3x minus 28 has to be larger or equal to 0. We know that this quadratic polynomial, x squared plus 3x minus 28, has 2 real zeros. Those zeros are x1 and x2. On the line of real numbers, they look like this: x1 at this position and x2 at this other position here. The coefficient paired with number x squared here is number 1. From the quadratic equation, ax squared plus bx plus c is equal to 0, that coefficient corresponds to the value of a. In our specific case, the value for that a is 1. When dealing with a function f of x defined as ax squared plus bx plus c, its graph is going to be a parabola. The question is, how is that parabola going to look like? We have an x-axis and we have a y-axis of the Descartes coordinate system. We have the values x1 and x2, which are the roots of the polynomial or the zeros of this quadratic equation here. If number a is larger than 0, that parabola is going to have a minimal value on its domain, and its graph is going to look like this. It passes through the dots x1 and x2 on the x-axis. This is the graph of the function f for a strictly larger than 0. As you can see, everything that is above the x-axis has the positive values on the y-axis. So, parabola has positive values in these sections. Left from x1 and right from x2. Where is it negative? It is negative on this section, and that is corresponding with the interval from x1 to x2. That is the interval which has the values below the x-axis. So, parabola has the positive values for x, which is inside the set from negative infinity to x1, union from x2 to positive infinity. The negative values are going to be achieved when graph of the function is under the x-axis, this area here. And that is the interval where x is from x1 to x2. Those are the negative values. Zeros, those are x1 and x2 dots. So in the quadratic equation ax squared plus bx plus c is equal to 0, zeros are x1 and x2. If a, the coefficient which stands next to x squared, is strictly smaller than 0, then the following happens. Again, we have Descartes' coordinate system. X and axis y, the origin, and we have x1 and x2. Our parabola is going to look like this when a is strictly smaller than 0. It is going to achieve the maximum value on its domain. So at this point, I will give you a little tip how you can remember what your parabola, what your graph of the quadratic function looks like. So you have a quadratic equation ax squared plus bx plus c is equal to 0. And you have found its zeros. Those are numbers x1 and x2. This is your parabola. This position here is x1 and this dot here is x2. So in ax squared plus bx plus c, if a is larger than 0, this is what your parabola, this is what your graph looks like. It looks like a smiley face, and that is how you can remember it. If a is larger than 0, you have a smiley face. If a is smaller than 0, you are going to have a sad face. x1 and x2 here, and the parabola has a maximum value on its domain. You see, it looks like a smiley face, and that is how you can easily remember it. Now let's return to our example. X squared plus 3x minus 28 is equal to zeros. We have found that the zeros are x1, negative 7, and x2, which is positive 4. We have our x, the variable which we are reading the values of on the line of real numbers. We have numbers negative 7 and 4. Ax squared, a is number 1, that is larger than 0. We have a smiley face. So let's draw that smiley face here. As you can see above the x-axis, those are the positive values, and below the x-axis, those are negative values. Our non-equality was x squared plus 3x minus 28 is larger or equal to 0. So we are going to take the parts of x-axis where function, our smiley face, is above the x-axis. Note that we have here larger or equal than 0. So we are going to include zeros in the intervals. Because zeros are included, we have these closed circles at these positions. Number negative 7 is included, and we are taking the positive values. Positive values are for everything that is left from number negative 7. We are taking all the positive values. Number 4. We have larger or equal than 0, equal, it means this number 4 is included. Larger, everything that is on the right side of it. And this is our interval. So x is inside an interval from negative infinity to negative 7. Negative 7 is included, union, number 4 is included all the way to positive infinity. And remember, we are looking only for finite dots. Negative infinity and plus infinity are not finite. That is why we can never include them in an interval. Let's do another example. It can happen that you have a fraction and the square root function combined in the same manner. Let's observe the function f, which is defined as 2x minus 7 over the square root of x plus 3. Again, our job is to find the domain of function f. If you recall, we have already done quite a few examples with fractions. In all of those examples, we had one condition that had to be respected, and that was the denominator of a fraction has to be different than 0, as division by 0 is not allowed. The same thing applies here. So the denominator, which is a square root of x plus 3, has to be different from 0. What we also have in this function is a square root function, and we know that in order for a square root function to be well-defined, its argument has to be larger or equal to 0. And that is how we get our conditions, which have to be respected in order for a function to be well-defined. So in this case, we have a conjunction of these two conditions. The square root of x plus 3 is different than 0, and x plus 3 has to be larger or equal to 0, because that is an argument of this square root function. So in the first case, when we square this, x plus 3 remains different from 0, and that means that x has to be different from negative 3. and in this case x has to be larger or equal than a negative 3. So let's put this on a line of all real numbers. We are reading the values for variable x from this line. Number negative 3 is at this position. It has to be different than a negative 3, so negative 3 is not included in our interval. X has to be larger or equal than a negative 3, so everything that is on the right side of the number negative 3 is inside our interval. So the interval is from negative 3 all the way to positive infinity, where number negative 3 is not included in that interval. Note here that we had the conjunction of these two conditions. That is why I have taken an intersection of these two sets which these two conditions correspond to. So finally, the domain of our function f is from negative 3 to positive infinity. Number negative 3 is not included in that interval. Another important example is going to be this one. Function f is defined as the square root of x minus 4 over x squared minus 25. The problem again is to find the domain of this function f. As you can see, we have a square root function here in the numerator, and for it to be well defined, its argument has to be larger or equal to 0. Therefore, x minus 4 is larger or equal to 0. Now let's observe the fraction. We know that division by 0 is not allowed, so the denominator of our fraction has to be different from 0. And that means that x squared minus 25 has to be different than 0. So we have the conjunction of these two conditions. The first condition is equivalent to x being larger or equal to number 4, and the second condition, x squared minus 25 is different than 0, means that x squared has to be different from 25. We are going to take a square root of both sides, so we have a square root of x squared to be different than square root of 25. As you know, the square root of 25 is equal to 5, not plus or minus 5. Remember, that is important. It is just number 5. And the square root of x squared is equal to the absolute value of x. Therefore, we have that absolute value of x has to be different from 5, and that is going to give us that x has to be different than negative 5, and x has to be different from number 5. I have already made a video in which I have explained why the square root of 25 is equal to 5 and not plus or minus 5. And I have also explained that the square root of x squared is equal to the absolute value of x. I have linked that video in the description here, and I strongly recommend that you watch it. Finally, we have our conditions. X is larger or equal to 4, and x has to be different from negative 5, and x has to be different from 5. Let's put all of this information on a line of real numbers. We have number negative 5, which is not included in our domain, and we have number 5 here, which is also not included in the domain. We have number 4 here, and we are taking everything that is larger or equal to number 4. Number 4 is inside of our domain, and we are taking everything on the right side of it. As you can see, we have the conjunctions of these cases, and that means that we have to take an intersection of their corresponding sets. Thus, we get that x is a value from the set from number 4 to positive infinity, which we are going to exclude from number 5. This can also be written as a set from 4 to 5 closed parenthesis, union from 5 to positive infinity. Number 5, as you can see, is not included in this set, and number 4 is included in this set. We have a square bracket to denote that number 4 belongs inside the interval, and we have a parenthesis here to denote that number 5 does not belong in an interval. Finally, the domain is from 4 to 5, union from 5 to positive infinity. Number 4 is included and number 5 is not included. Let's now work through an even more complicated problem. Function f is defined as a fraction. In the numerator we have a square root of x plus 3, and in the denominator we have the square root of x squared minus 16. Again, our job is to find the domain of this fraction. Let's first focus on the numerator. We have a square root function in it, and we know that in order for square root to be well defined, its argument has to be larger or equal to 0. Therefore, x plus 3 has to be larger or equal to 0. Let's observe the function f again. We can observe this function, and we know that in order for fraction to be well defined, division by 0 can't happen. Therefore, the denominator of a fraction has to be different from 0. That means that the square root of x squared minus 16 is different from 0. If we take a look one more time at our function f, we can observe that in the denominator of a fraction figures a square root function. In order for a square root function to be well defined, the argument of that square root function has to be larger or equal than 0. So x squared minus 16 is larger or equal to 0. We now have a conjunction of these three terms. So every single one of these three conditions has to be satisfied in order for function f to be well defined. That area in which the function f is well defined, we call a domain of said function f. The first term, x plus 3 is larger or equal to 0, is equivalent to x being larger or equal to negative 3. In the second condition, we have the square root. We can square both sides of the inequality, and that will give us that x squared minus 16 is different from 0, which means that x squared has to be different from 16, and that means that x, the square root of x squared, has to be different than the square root of 16, and then the absolute value of x is different than a number 4. X is then different than a negative 4, and x is different from number 4. We have a conjunction of these cases. So this is our first case, this is our second case, and finally let's observe the third case. The final condition, x squared minus 16 is larger or equal to 0, is equivalent to x squared being larger or equal to 16. That means that the square root of x squared is larger or equal than the square root of 16, and that means that the absolute value of x has to be larger or equal than the number 4. This will give us that x has to be smaller or equal to negative 4, or x has to be larger or equal to 4. This is not and, this is or. My mistake. So finally, let's put all of this into one sentence. We have that x is larger or equal than a negative 3, and x has to be different than a negative 4, and x has to be different than 4. We have this conjunction, x is smaller or equal than negative 4, or x is larger or equal to 4. Let's put all of this information on a real line. We have a line of real numbers. We are reading the values of a variable x from it. The first condition is x has to be larger or equal than a negative 3. Number negative 3 is at this position. larger or equal, that is everything on the right side, and we are going to include the number -3 in this interval. The next thing which we have is a conjunction, and notice here that these conjunctions mean that all of these conditions have to be satisfied. That means that we are going to find our answer as an intersection of all of these sets of numbers represented here on a real line. We have the next condition that x is different than the number -4. So we are going to represent this with this empty circle at number 4. The next condition is that x has to be different from 4. Again, this is number 4, and we are going to represent that with an empty circle at number 4. We have conjunction again, and we have this bracket here. X has to be smaller or equal to -4. That is all the numbers on the left side of -4, and this -4 is included. And we have or, that means the union of the set where x's are larger or equal than 4. That means everything that is on the right side of the number 4, including the number 4. So this is one set. How are we going to deal with this? We have a conjunction, and that means that we are dealing with an intersection. So we are going to observe this as one set, and we are going to take the intersection of that set with this set where x is different than -4 and x is different than a number 4. So we have the sets from -4 to the -infinity and from 4 to +infinity. These numbers -4 and 4 are not included. And finally, we have an intersection with x which is larger or equal to -3. This set right here, this interval. When we take the intersection of that, intersection of this on the left side is going to be an empty set. We can only intersect it with what is on the right. So we are going to intersect from the -3 to +infinity with numbers from 4 to +infinity. And that is how we get that x belongs inside the set of 4 to +infinity. This here is a parenthesis noting that number 4 does not belong in this set because of this empty circle right here. Finally, our domain is all the values from 4 to +infinity. 4 is not included. So in this video I have shown you how to find the domain of a function, in particular linear function, polynomials, rational and square root functions. I hope that you have enjoyed this video and found it to be somewhat useful. If that is the case, please subscribe to my channel, like and share, as your support means a lot to me. I'm looking forward to reading your comments, and I suggest that you watch this video next.